In the next section, we want to see how we can make binary search dynamic. And what will be the solution for this is called a binary search tree. So here's the question I already started before. Most of you already had a chance to answer. And because it's quite clear, let me also log it now and show the results. So the second is the answer I was after. A binary search tree is a binary tree as well. So the first answer is not wrong, but it's not all there is to it. This one was a heap, so heap ordered trees are no longer a thing in this chapter. And yeah, this last point, I should have maybe discussed this when we discussed the question for heaps as well. So there's the same term heap used for different things in computer science, as you may be aware. Binary heaps is the data structure we discussed in the last section, where we can do insert and delete the max and these things. There's also a heap area in programming languages where you can dynamically generate objects. Whenever you call new in Java, you generate an object on the heap. In Python, pretty much everything is an object, and they're all allocated on the heap. It's just a separate piece of memory that you can allocate chunks of it and use it for objects. It has nothing to do with the heap data structure. In particular, the heap space is not organized like a binary heap. It's just a very generic term, something to be aware of. OK, what is a binary search tree then? It is a binary tree, so every node has 2 children, and it has keys. And the important property is spelled out here. And again here, so the nice red box is what you should keep in mind. If you have a root of the binary search tree, it has a certain key, then this key must be bigger than everything that's in the left subtree and smaller than everything that's in the right subtree. And you can also phrase this just about looking at the children, and then recursively it holds for the entire tree. I think the way you should think about binary search trees is really, this is binary search made dynamic, so that you can change the array. And because we can't really change the array, what we instead do is work with pointered structures. So the typical way to represent a single node in a binary search tree would be to have some object that has a key and a value, and 2 pointers, one for the left and one for the right child. And then, well, we can have many more nodes. Didn't copy the box. So maybe this has a pointer to those 2 guys. So the left points to this, and the right points to this. And then these can have, again, more children, etc. Until at a certain point, the pointers are null, which means there's no further children. OK, I think in one way or another, I hope you have seen this. You could implement it exactly like this, for example, in Python. Here's an example of how I want you to think about binary search trees. So in the computer, it's just an object, a collection of objects with pointers, and there's left and right child pointers. We don't usually need a pointer to the parent, although some implementations do this because it makes some operations easier or more efficient in some cases. For what we discuss in this class, you don't need them. You only need pointers to the children. And I really want you to think of a binary search tree always drawn like on this picture. If you have the root, it projects down its key onto a certain x position, and then the 2 subtrees shouldn't overlap in x direction. If you do this at all positions, then what you project down is the keys in sorted order. Now, this is just our imagination. In the computer, these are just pointers, and there's no specific way to lay them out. But if you draw them like this, most of the algorithms become really intuitive. So always do it like this. I wish all books would do it like this. but alas. So let's do an example how you can find elements in this tree, say 69. You always start at the root because actually the root is the only thing you really have a pointer to. So the data structure consists of these objects and the pointer to the root. So you start at the root. Now you compare your key 69 to the key in the root. And of course this is smaller, so you follow the pointer to the left. Because remember, binary search tree property, all the keys on the right are bigger than the root key, so they cannot possibly be where the 69 is stored. Okay? Now we find 12 is too small, so this time we follow the right pointer. And again, this is too small, so we follow this one. And here, yay, we found 69. So we would, in that node, remember, we don't only store the key, we also store a value, so we can return the value and return it, or do whatever we wanted with this operation. One more example where the search fails. So suppose we try to find 83. We start at the root. It's bigger than 77, so we go right this time. It is smaller than 85, so we go left. It's bigger than 80, and it's bigger than 82. And at this point, we reach a null pointer. So that means there is no further thing in the tree. There is nothing between this range. So the last time we went left and the point where we go right here means this is the range that we know. There's no key between 82 and 85 in this dictionary. So we can return to the user, sorry, that key doesn't exist in our dictionary at this point. Okay? I call this operation find because it's used as a subroutine in the other operations as well. But one thing you can implement with this is get, the ADT operation. All right. If you think about this, what we're doing here, this is really a binary search on this array down there. Just that we don't always jump exactly to the middle, but we jump to wherever the root happens to be. But still, in either case where we made a comparison, we excluded one part of the tree. That's the same as in binary search. Now, the interesting part about binary search trees is that we can change them. We can insert things without copying array elements over. So let's briefly see how we can do that. Suppose we want to insert 88. The first thing we do is try to find it. That's the same procedure as before. We only allow to insert it if it's not already present. And in this case, we end up at this leaf. So find says it's all right, 88 is not already in the tree, so you can go ahead and insert it. So that's the first step. You know this leaf now. And in a sense, you're just replacing this null pointer with a new node. But to draw it nicely, I just first swap this over. So this is just moving the node out, as you can hopefully see. Leave some space. Then we put in this new node and link it into the tree. Okay? Good. That's insertion. And last thing is we can also delete elements. That's the most tricky operation of the three, so it has different cases. Let me just briefly run through those. Again, I think many of you will have seen this, but if not, this should give you enough of an idea to understand how these work. If we want to delete 11, well, first we search for it. Same as always. In this case, 11 is a leaf. Both children are null, so we can just get rid of it, and that's it. Okay, so we set this pointer to null and delete this node. That's all we need to do to remove 11. A slightly harder case is if we end up at a node that has one child, like in the case of 69. In this case, we can't just remove this node because then we would leave this subtree dangling in thin air. What we instead do is we rewire the right edge from the parent to point to this single subtree that is now parentless. So the parent of 69 adopts this subtree. But then that's also an easy case because it's just a local change. The most tricky one is when we want to delete a binary node, because in this case, if we got rid of this, there's two subtrees that now need a parent, and we kind of don't have two pointers left. We only have one parent pointer to spare. So the standard way to solve this is to find the predecessor in the tree of this key, which means you want to find the first one that's to the left. And you can do this by once going left and then go right as long as needed until you find a null pointer. That must bring you to the predecessor key. And so what you do then is you take this node, take this one and just move the 82 into here. And then you have to recursively delete this node. But that, by definition, has a single child at most because the right child was null. So this is never again the tough case. It might just be the medium case again. And in this case, it's actually a leaf, so nothing happens. Okay? That's how you can also remove nodes from binary search tree again. Let's briefly see how expensive all of these operations are. And then I promise we'll do a little break. So for search or operation get in the ADT, all we did was the find operation. And remember, find started at the root and made its way down the tree. And at every node, we did one comparison until we arrive at some point where either the search stops because we have found the element or we reach a null pointer. So the cost is pretty much the height of the binary search tree. It's never more than the height because that's the longest possible path you could have. And the number of comparisons is the length of the search path, maybe +1 for finding the actual key where you get. And so again, this is at most the height +1. And so all we can say for now is if h is the height of the tree, then the cost of finding an element or finding a node in the tree has cost at most h, or order h, big O of h, if you want to be less precise. For an insertion, remember how insertion worked. There were two steps. First, we find the position where we want to insert, and then we only really create a new node and wire it in. So the second step is just rewiring a few pointers and allocating a new object, but that's a constant amount of effort. It doesn't depend on how big the tree is. And the first step is, again, find. So again, the cost is essentially dominated by the height of the tree. And for delete, if you think about it again a bit more carefully, it has these separate steps. Let's say the hard case happens. You search some node, then you find it, then it's a binary node, so you have to further find its predecessor. But again, if you take the two find steps together, they both together give a path. from root to some node, to some predecessor node. And that's again bounded by the height of the tree because you can't go further down. So it's 2 times find, but they actually together are one path. And more constant effort because you rewire pointers and delete a node. But again, the effort is essentially bounded by the height. And so here I summarize this nicely in a table again. The construction for binary search trees, unlike for heaps, we don't know anything smarter than inserting things one after each other. And all the other operations are bounded by the height, except for the very simple ones. So that brings us to the question, what is the height of a binary search tree? And unfortunately, in the worst case, it's really, really bad. You can see this if you insert the elements in sorted order. You would always find the next insertion would always go to the rightmost elements. Say we try to insert 5 here. It's bigger than this, bigger than this, bigger than this, bigger than this, bigger than, okay, and here's the null pointer, so here it should go. And it's clear you can keep going like this. So in this case, the binary search tree deteriorates to a linear linked list. That's really terrible. So in the worst case, the height can be linear. So why all the fuss? Why do people still like binary search trees? There's 2 answers, but the first answer is, if you look at the average case, then this doesn't happen. If the insertions come in random order, then you can show that the height is logarithmic. And you can even make a stronger statement. For the experts, we say with high probability, the height is logarithmic, and it's spelled out here in detail what I mean precisely by that. And there's interesting proofs behind this that we'll skip. But in a sense, if you have any reason to believe that your keys come not in the worst case order, but there's some randomness in the process, you will not see such a high binary search tree. It almost always is fine. Okay.